A very warm welcome to the 7th lecture on the subject of wavelets and multirate digital signal processing. Recall that we had ended the previous lecture by hinting at the structure of the synthesis filter bank corresponding to the Haar multi-resolution analysis. Today, we begin by looking at both the analysis side and the synthesis side once again. I mean the analysis filter bank and the synthesis filter bank in the Haar multi-resolution analysis. So, let us put down the two filter banks clearly. You will recall that on the analysis side, we had a structure like this. We had the sequence, let us call it x of n, corresponding to the function in V1. Essentially, it was subjected to the action of two filters, a filter of the form half 1 plus Z inverse another one of the form half 1 minus Z inverse followed by a downsampling by 2. We had also derived the structure of the synthesis filter bank, and interestingly we saw the structure was very similar. In fact, it looked almost like a mirror image here. Except for the fact that you had an upsampler instead of a downsampler. Followed by the two filters once again. So, here the filters had the form 1 plus Z inverse and 1 minus Z inverse. Now, the only catch is I am going to allow for an ambiguity of sign here, plus minus 1 minus Z inverse. A small variation from last time, a subtle point, but important. Now, there are several things to which we must pay attention. One is, if you look at the structure of the analysis and the synthesis filter banks, the filters are almost identical. These are the two filters for the analysis side and these are the two filters for the synthesis side. Please note, I am allowing an ambiguity here. What would the physical meaning of the ambiguity be? It would just determine where I place the sum sample and the difference sample. With a plus sign, the sum sample will get placed at the even locations and the difference sample at the odd locations. With a minus sign, it would be the other way around. So, let us leave that ambiguity for the moment. If we try and resolve the ambiguity right away, we might actually get more confused. So, allowing that little ambiguity for the moment, let us analyze this whole structure in general and then resolve the ambiguity. Anyway, coming back to the filter bank structure as we see it, one very beautiful thing that we notice about the Haar filter bank is that the filters on the analysis side and the synthesis side are almost the same, except for this sign ambiguity. And if we really look at it, these two filters are also very meaningful in another domain, of which we shall soon have more information. Now, what we are going to do from here onwards is to look at this general structure. You see, we want to understand why the Haar multi-resolution analysis, though attractive, is not adequate. I have been saying all the while that if we understand the Haar multi-resolution analysis and if we understand the filter bank corresponding to the Haar multi-resolution analysis, we understand quite a great deal about filter banks and multi-resolution analysis. Most of the concepts are captured. Then why should we look for other multi-resolution analysis? That is a subtle point, which we shall see by going into another domain now. So, our objective here is to look at the frequency domain behavior. And how would we get a frequency domain representation of the Haar filter bank? So, what we will do is we will progress as follows. First, we shall look at the frequency domain for the filter bank. And how would we do that? We would do that by substituting z equal to e raised to the power j omega. Let me once again recapitulate a few concepts from discrete time signal processing for the benefit of the class. Although one would have done these in a course on discrete time signal processing, it helps to put some of this discussion in perspective. You will recall that we had defined the Z transform last time. We had said that if you have a sequence x of n, its Z transform is capital X of Z defined by summation n running from minus to plus infinity x of n z raised to the power minus n, with z belonging to a region of convergence. Now, in particular, if the region, so let this region be script r. In particular, if this region includes the unit circle. So, let me say a little bit about the regions of convergence of a typical Z transform. Typically, R has the following patterns. R is between two circles centered at the origin. So, it has an appearance something like this, and both of these are centered at the origin. So, you have R 2 and R 1. So, here the radius is R 1 and here the radius is R 2. Now, it could be true that R 2 might be infinity or R 1 might be 0. So, we have to allow these possibilities. Most generally, R 1 could be 0, R 2 could be infinity. Moreover, the boundaries may or may not be included. The boundary circles may be included or excluded. In fact, if these values R 1 and R 2 are non-zero and finite, most of the time the boundaries are excluded. It is only when R 2 becomes infinity or when R 1 becomes 0 that there is a question. Is the boundary included or excluded? And that is not a trivial issue. Whether the boundary is included or excluded makes a difference to the properties of the system. Well, all this essentially to recall a few points about the Z transform, and now coming to the frequency domain. So, in particular, if the unit circle, that is mod z equal to 1, it is a circle, you see, mod z equal to 1 is a circle of radius 1 in the z plane. So, if the unit circle is included in R, then we have a frequency response for the system. The system has a frequency response. That is, you see, we talk about the system having a frequency response if the underlying Z transform is a system function. If the underlying Z transform is a system function. And of course, otherwise, in case we are talking about a sequence, then we say the sequence has a discrete time Fourier transform. So, if we are talking about the Z transform of a sequence, we say the sequence has a discrete time Fourier transform. This is an important concept, a DTFT for short. Either way, what we are saying is, in case the unit circle is included in the region of convergence, then we have an even more interesting interpretation of the system function or the sequence in question. And in fact, if we look at all these Z transforms encountered in the Haar filter bank, they all satisfy this.